Hello guys, my name is IBM and today I want to record Physics 9702 paper 5. This is planning, analysis and evaluation. This is May June 2024. One student has been asking me a lot to record this paper. So the paper is supposed to be 1 hour and 15 minutes, but because I do this on a computer, it may take much time because I also have to explain how I arrive at several answers. So my name is IBM and I just want to show you how I encourage my students to always approach this paper 5. So straight away, let me go to the first question. A spring is attached to a cylindrical magnet of length L. So it means our students will be able to measure the length. To measure the length, maybe the student may decide to use a ruler and cross-section area A. So this is a cylindrical magnet, so the cross-sectional area is A, and the cross-sectional area is going to be the area of a circle, which is going to be pi d squared over 4. So that means the student will have to measure the diameter. So the student will have to measure the diameter using may use a micrometer screw gauge or a digital vernier caliper. I'll just take a micrometer screw gauge. But of course, while measuring the diameter, the student will take measurements along the cylinder and obtain the average diameter. So I have this one mark 2, 3 and 4 marks already in my head that I know that I must cover those 4 marks. The magnet is placed on a thin card on top of a magnetic sheet. So the magnet is placed on a thin card on top of a magnetic sheet as shown in the figure. The thickness of the card is T. So how will I measure the thickness T? Of course, I'll measure the thickness T using a micrometer screw gauge. And also I'll measure at different points and obtain the average of T. The magnetic flux density at one pole of the magnet B is B. Of the magnet is B. So how do I measure the magnetic flux density? To measure the magnetic flux density, a student knows that they will use a Hall probe. And remember, when using a Hall probe, you measure first in one direction, then in another direction, and then obtain the average. So we'll get the average value of B. Using a Hall probe, we measure B in one direction, then we measure B in the opposite direction and obtain the average. Or you can just rotate the Hall probe until you get a maximum value of B. Then a force is applied upwards to the string. A force is applied upwards to the string. The extension of the spring, when the magnet just leaves the card, is S. So of course, to measure this extension, we need a ruler, which we are going to clamp. So I'll add a ruler here, which is going to be clamped. So on this is just a sketch of the diagram. I'll clamp the ruler here. Of course, this is going to be a plastic ruler because it is involving a magnetism. So this is going to be a plastic ruler. Also, to prevent the magnet from being attracted to the stand, I'll also use a wooden stand with a wooden clamp. So this is the clamp. This is just a rough sketch before I will sketch a better diagram. So let's say this is a wooden clamp and let's say this is the stand. It should also be a wooden stand. So this is going to be a wooden stand. And this should be a wooden clamp. The reason is because I know the magnet may be the magnet may be attracted to one of them. This is also going to be a plastic ruler. Okay. Then to measure the thickness, of course, I'm going to use a ruler. So the best thing would be to attach a pointer So let's say this is a pointer, because I may want to find the initial position of the pointer on the ruler and the final position to subtract to find the thickness, the extension x, the extension e. So those are the measurements. So I'll find the new position of the pointer minus the initial position of the pointer to find s. New position of the pointer minus new position of the pointer minus the initial position of the pointer is going to be equal to s. Okay. Then or you would find you would measure the original length of the spring, call that one L naught, and then you find the new length of the spring, then you subtract to find the extension. So extension can also be L1 minus L naught. But I will just use new position minus final initial position. Then it is suggested that S is related to T by the relationship. So of course, if we change the thickness of the card is T. Of course, if the thickness changes, we expect that S is going to be changed. So that means T is going to be the independent variable and S is going to be the dependent variable. So S is the dependent variable and T is the independent variable. Okay, it is suggested that S is related to T by that relationship, where K is the spring constant of the spring and Z is constant. So K is the spring constant. So remember, finding the spring constant, F is equal to K times X. So K is going to be F over X. So I must describe an experiment to find K. Then Z is a constant. Plan a laboratory experiment to test the relationship between S and T. So first of all, of course, the cross-sectional area should remain constant. The length is going to remain constant. We shall also make sure that the magnetic flux density is constant. So ALB should remain constant. Then I should also make sure that K is kept constant, and I should also make sure that the limit of elastic limit is not exceeded. So K should remain constant and the elastic limit is not going to be exceeded, because if it is exceeded, it is going to affect the values of S when T changes. Then draw a diagram. I'll draw a better diagram. Explain how the results could be used to determine a value for Z. So because we are varying T and recording S. So T is the independent variable, and we always put the independent variable or something related to the independent variable on the x-axis and something related to the dependent variable on the y-axis. So I'll try to make K the subject. S the subject. So S is going to be equal to A, L, B, Z divided by K times 1 over T. So the easiest graph to plot is going to be S against. I'll plot S against 1 over T. And of course, this is a straight line. There is no y-intercept, so it is through the origin. And then to find Z, the gradient is going to be equal to ALBZ over K. Because when we compare this with the y equals to mx plus c, there is no y-intercept, so the gradient is going to be ALBZ over K, which means our Z is going to be equal to K times the gradient divided by ALB. Okay, so I think that skeleton is enough for us to now write an essay. But before I write the essay, I may so in this I may just identify I may first write the independent and the dependent variables. So I'll say in this experiment, T is the independent variable and S is the dependent variable. Alternatively, you can say in this experiment, I will vary T and measure S, because we vary the independent and we measure the dependent. Then I also said I will keep K constant, where K is the spring constant. I will keep K constant. I'll also ensure that A, L, and B remain constant. A, L, and B should also remain constant. Okay, so I will first draw the diagram. My diagram may not be very accurate, may not look so nice. It may not look very nice because it is on paper. But one thing I forgot to mention is that I may add, because I know when I try to lift the magnet, the magnetic sheet may also move upward. So I have to fix it on the table using maybe G clamps. Fix this on the table using G clamps. Okay. So I'll draw, or I'll sketch a diagram. You can draw a better diagram. So let this be the table or the bench. So this is the bench. And then I'll start by putting here the magnetic sheet. So that is the magnetic sheet. Then I'll add the card. So this is going to be the card. Then I'll put my cylindrical magnet. Then on the cylindrical magnet, of course, I have to attach a spring. Then on the spring, I said I will attach a pointer. Let's say the pointer is somewhere here. Then I have to put a G clamp somewhere here. So whichever way you draw the G clamps, as long as you label them G clamps. So that is the G clamp, which is holding the magnetic sheet. So this is the magnetic sheet. And this one is the card. And this is the cylindrical magnet. Remember, I'm going to apply a force to lift the magnet. So I will need now a ruler which is clamped somewhere here. So I'll draw a ruler. So this ruler must be held vertical with a clamp. So that is the ruler, it's going to be a plastic ruler. Then this be a wooden stand. Of course, even the base should be wooden. Let this be a wooden clamp. And that means I will also make my G clamps to be wooden G clamps to prevent the magnet from attracting or being attracted to or attracting any of those during the experiment. I think I've exhausted all I needed for this experiment. I've named everything necessary. Yeah, so now I can now write my essay. I've already written the skeleton of what I'm going to include in my essay, so now writing becomes easy. Let me try to use around 10 minutes to write the remaining part. So to collect and analyze data, I will take the following steps. I'll take the following steps. Step number 1, I'll measure the length L of the cylindrical magnet using a ruler. I will measure L using a ruler. Step number 2, I'll measure the diameter D of the magnet using a micrometer screw gauge. And of course, I will repeat, here I'll just put an outline. I will repeat measurements of D at different points along the cylinder. I will repeat measurements of D at different points along the cylinder and obtain the average value of D. So I will obtain the average. And of course, after obtaining the average, now I can obtain the cross-sectional area. So I will determine A from A equals to pi d squared over 4. That is the cross-sectional area. Okay, so step number 3. So I have finished to find the cross-sectional area from pi d squared over 4. So step number 3, I'll now measure, I think, the thickness of the card which I'm using. So I will measure the thickness of the card T using a micrometer screw gauge. And of course, I'll repeat measurements of T in different positions on the card. I'll repeat measurements of T in different positions on the card and obtain the average value of T. So I've measured, of course, here there are 2 marks, I think, in one, measuring the thickness using a micrometer screw gauge and measuring T in different positions and obtain the average. Then I think next is to measure the constant. So step 4, I'll measure I think for the constant K, I will need a Newton meter to measure the force applied to the spring, and then I determine K from K equals to the force over the extension. So I will use a Newton meter to measure the force applied to the spring, and determine K from K equals to the force divided by the extension. So I just put a force on this, I just apply a force on the spring and then determine the extension, and I get K for the spring. Alternatively, I would take several readings of force and extension, and then I plot a graph of force against extension. Then I obtain the gradient, that will be the constant. Alternatively, I could also find K from mg divided by the extension. I could just attach masses, and then I obtain K from the weight over the extension. Okay, but I'm just taking that using a Newton meter to determine the force applied, and then divide it by the extension to find K. Then step number 5, I will measure B. I will measure B using a Hall probe. A Hall probe in one direction. I'll measure B using a Hall probe. Let me say first in one direction, then in the other, in the opposite direction, and obtain the average value of B. Okay, now what remains is just to set up the apparatus and then apply force. So step 6, I will set up the apparatus. As shown in the figure, or as shown in the diagram. Step 7, I'm going to apply force. So I will apply a force on the spring. This should be gradually, so that the force on this should be gradually until the magnet just leaves the card. So I'll apply the force on the spring, gradually increasing the force, or slowly increasing the force, on the spring until the magnet just leaves the card. Until the magnet just leaves the card and then obtain S. And of course, I'm going to obtain S from the new position of the pointer on the ruler minus the initial position of the pointer on the roll. Remember I said you would measure the length, the original length of the spring, and then the new length of the spring, and then obtain the difference. Then step number 8, I'll repeat measurements of S for the same, of course I have to repeat the measurement for S for the same value of T and obtain the average. So I will repeat measurement of S for the same value of T and obtain an average value of S. So remember, you should always check and see that the limit of the elastic limit has not been exceeded. So I also have tried this one here. I will remove the force and check if the spring returns to its original length. I will remove the force and check if the spring returns to its original length every time, so that the elastic limit is not exceeded, so that the elastic limit is not exceeded. Okay, so you have always to ensure that the elastic limit is not exceeded. So the only way you can do that is to remove the deforming force and see if the material goes back to its original length. Then now for the analysis part, of course I have to repeat measurements of S for different values of T until I have about 6 sets of values. So I will repeat measurements. I'll repeat measurements of S for different values of T until I have until I have 6 sets of values. So I will repeat measurements of S for different values of T until I have 6 sets of values. Then step 11, I think that should be analysis. Which graph will I plot? So I said already that I will plot a graph of S against 1 over t. Of course, we expected that this is a straight line, so a straight line through the origin shows that the relationship is valid. So a straight line through the origin shows that the relationship is valid. A straight line through the origin shows that the relationship is valid. And then, of course, the gradient. The gradient was equal to ALBZ divided by K, which implied that Z was equal to the gradient multiplied by K divided by ALB. Then the last part is for safety. Let this be 12. So I'll say for safety, why isn't the space enough? Where should I write now? Okay, I'll write on this page. So for safety, I'll put a safety screen around the experiment, because most likely the spring may jump into your eyes or the magnet. So I'll put a safety screen around the experiment in order to protect my eyes from being, let's say, hit by the spring or magnet. The spring could jump off and hit the eyes, or the magnet could jump off and hit the eye. So a protective screen or a safety screen around the experiment could be necessary. So I'll put a safety screen around the experiment to protect my eyes from being hit by the spring or the magnet. Okay, so I will not read through the essay. In case there is any spelling errors, you can try to rectify that. Question 2. A student investigates the resonant frequency of a metal rod. The metal rod of length L is suspended from two rubber loops. A sensitive microphone with a cone is positioned at one end of the rod. The microphone is attached to an oscilloscope as shown in the figure. The rod is hit gently with a hammer. The period T of the trace produced on the oscilloscope is determined. The experiment is repeated for different values of L. It is suggested that T and L are related by this equation. A graph is plotted of log of T on the y-axis against log of L. So I'm going to introduce log on both sides. So it will be log of T equals to log of 2 over CL power n, which is the same as log of 2 over C plus log of L power n. Therefore, it means log of T is going to be equal to log. This is going to be log of 2 over C plus n log of L. So when you rearrange, you have log of T equals to N log of L plus log of 2 divided by C. When you compare this with Y equals to mx plus C. So on the y-axis, you have log of T. On the x-axis, you have log of L. So it means the gradient is going to be equal to N. The y-intercept is going to be log of 2 divided by C. Okay, log of 2 divided by C. The values of L and T are given in the table. Calculate and record values of log L in centimeters and log of T in the table. Include absolute uncertainties of log of T. So for log, we shall just maintain the, of course, for logarithm, when you find the log of a number, the number of decimal places becomes the number of significant figures. For example, here we have, the number of significant figures becomes the number of decimal places when you find the log, but the rule allows you to write more decimal places. So we have here 2 significant figures becomes 2 decimal places. For example, I have the log of 54. I'm finding log of L, log of 54. That is 1.73. So I'll write 1.73. Then I'll find the log of 70. That is 1.85. Then I will find the log of 86. That's 1.93. Then I will find the log of 108, which is 2.033. Remember, here we have 3 significant figures, so this becomes 3 significant figures becomes 3 decimal places. That is according to the rule. The number of significant figures becomes the number of decimal places when you find a logarithm. So next, we have log of 104, which becomes 2.1. Sorry, I found the wrong log. Log of 140, not 104. 2.146. Then the last one is the log of 167. That is 2.223. Okay, then we can now find the log of t. I don't need to find the power to use the power of 10 because we look at the labeling. The power of 10 has already been incorporated in this bracket here, so I don't need to use the power of 10. So I'll just simply say log of 24. Log of 24 is 1.38. The number of decimal places, the number of significant figures becomes the number of decimal places. So this is going to be 1.38. The rule allows you to write more, but not less than that. The next one is a log of 32. That is 1.51. The next one is log of log of 39. That's 1.59. The next one is log of 49, 1.69. The next one is log of 64, which is 1.80. It is 1.81, not 80. So it's 1.81. The next one is a log of 74, which is 1.87. So they told us to include the absolute uncertainties in log of t. So to find the absolute uncertainty in log of t, we can get the log of the highest, the log of a number. For example, for t, this would be the log of t maximum, which is going to be log of 24, 2 plus 1, which is log of 25, minus the log of 24. Or I can get a log of 24 minus the log of t minimum, which will be 24 minus 1, which is log of 23. The answers will be approximately the same. So I'll just now press my calculator. For the first one, it is going to be a log of 25 minus log of 24. So that is 0.00177 to one significant figure. It is going to be 0.02. Then the next one is going to be log of 32 plus 1, which is log of 33, minus log of 32. So that is, sorry, I didn't subtract. Log of 33 minus log of 32. That is 0.01. The next is log of 40, that is 39 plus 1, then minus log of 39. So this is also 0.01. The next one is log of 49 plus 2, that is log of 51, minus the log of 49, which is 0.02 to one significant figure. The next one is log of 64 plus 2, that is log of 66, minus log of 64. That is 0.01. Then the next is log of 74 plus 2, which is 76, log of 76, minus log of 74. So that is also 0.01. So finding uncertainties in logarithms are the easiest. You can get log of the highest minus log of the exact or the most likely value, or the log of the most likely value minus log of the minimum value, or it can be log of, this could have been log of 25 plus log of 23 divided by 2, but that would be wasting a lot of time. Log of the highest plus log of the lowest, sorry, minus, not plus. Log of the highest minus log of the lowest divided by 2, but that's a wastage of time. This one is fine, this one is fine, even this one is fine. So determine the gradient of the line of best fit, include the absolute uncertainty in your answer. Let's first plot a graph. So I tried my level best to make sure that the graph fits on the same page. So I have written the values down so that plotting them becomes easy. We are plotting log of t on the vertical, so the error bars are going to be vertical. Okay, so the first value is, or the scale Let's first find the scale. On the x-axis, it is 1.8 minus 1.7 divided by 10, which is 0.01. On the vertical axis, it is 1.4 minus 1.35 divided by 10. That means it is 5 times 10 to the power of minus 3. So this is 5 times 10 to the power of minus 3, one small square. Okay, so the first point I'm plotting, you can plot a better graph. This is just for guidance. Because I'm plotting this on a calculator, it may not be perfectly accurate. The first point is from my values that I've written, we have 1.38 plotted against 1.73. So this is 1.7123. Then 1.38. I'll just use my calculator to actually get 1.38. 1.38 minus 1.35. Then I divide this by the scale, which is 5 exponent minus 3. So I'm going to add 6 small squares from 1.35. So 5, 6. So this is going to be the point. The next one is 1.85 on the x-axis against 1.51. So 1.85 I think is in the center against 1.51. So 1.51, I'll use my calculator to be very accurate. 1.51 minus 1.5 divided by the scale, which is 5 exponent minus 3. Those are two squares, so this is going to be 1, 2. So this is the point. The next point is 1.93 against 1.59. So to be careful, I will use my calculator to plot 1.59 minus, it is above 1.55, divided by the scale, which is 5 exponent minus 3 on the vertical. Those are 8. So 1.93 against 1.59, I mean 1.93 against 1.59, those are 8 small squares, so my plotted point is going to be here. The next is 2.033. I'll use a scale to be very careful. 2.033 on the x-axis against 1.69. So 2.033 minus 2 divided by the scale. The scale is 0.01 on the x-axis, 0.01. So I'm going to add 3 small squares and approximate in the center. So 3 small squares and approximate in the center. Then on the vertical I have 1.69. 1.69 minus, it is just above 1.65. Divide by the scale on the vertical, which is 5 exponent minus 3. Those are 8. So I'm going to add 8 small squares on 1.65. So 1, 5, 6, 7, 8. So this is very close to this point. It's not exactly in the center, but is somehow here because the other one was 2.3. Okay. Then the next one is 2.14 against 1.81. 2.14. So 1 for those of 2.14. Okay, I'll use a calculator to be careful. 2.146 is just after 2.4, so I'll say minus 2.1. Divide by the scale, which is 0.01. So I'll add approximately 5 small boxes. almost 5 small boxes, up about 2.15. Then on the vertical, I have 1.81. So I'll say 1.81 minus, this is just above 1.8, divide by the scale, 5 exponent minus 3. I think that is 2 boxes. So those are 2 boxes. So the point is going to be somewhere here. Okay. Then the next point is going to be 2.223 on the x-axis. 2.223 on the x-axis. It is just after 2.2, so I'll say minus 2.2. Divide by the scale on the x-axis, 0.01. So I'll add around 2.3 boxes on the x. Then on the y-axis, I have 1.87 minus. It is above 1.85, so I'll say minus 1.85. Divide by the scale, which is 5 exponent minus 3. Those are 4. So 4 and 2.3 on the x-axis. So 4, 2.3. So 4, 2.3 is around here. Not exactly in the center, but closer to 2 boxes on the x-axis. So it is around there. Okay, so I've tried my level best. You could draw better, you could plot the points in a better way. But at least you can see the pattern that they are almost forming a straight line. So the next thing is just to balance these points, or I can even plot the error bars first. But anyway, let me first draw the line of best fit, because if I plot the error bars, then it becomes a problem when I want to rub. So I'm trying to fit the points on the same page so that I can easily make some good judgment. My judgment is not final, because if I could spend a whole day trying to make a judgment to draw a better line of best fit on a computer, which is really very hard. So I'm just going to draw a line for guidance. However, when drawing the line of best fit, try your level best to balance the points above and below the line. Okay, I will not redraw the line, but this is not the best line. This line could be slightly rotated anti-clockwise, I think. But you can draw a better line. This is just for guidance. I don't want to repeat this to take much of my time. Then I'm going now to plot the error bars. This is going to be the line of best fit. Let me plot the error bars. The error bars are vertical because we are plotting them for log t, where t is on the vertical. Remember, the scale on the vertical is one small square representing 5 times 10 to the power of minus 3. So we want to plot 0.02. How many boxes are 0.02? 0.02 divided by the scale, which is which is 5 exponent minus 3. I think those are 4 boxes. So if 0.02 is 4 boxes, 0.01 are going to be 2 boxes. So I will not again repeat calculating. So here 0.02, those are 4 boxes. So I will count 4 from the plotted point, and I count 4 downwards. 2, 3, 4. Then I will draw the line through them. That's one error bar. Then the second one is 0.01. Those are 2 up and 2 down. Then I'll draw the error bar. Then the next one is also 2 up and then 2 down. 2 up and 2 down. Then I'll draw the error bar. The next one is 0.2, which is 4 up and 4 down. So 1, 2, 3, 4. And 4 down, 1, 2, 3, 4. Then I'll draw the error bar. You can draw a better error bar, but you can always pass the pencil there at least twice to make them bold. Then the other one is, this error bar is not very accurate, but you can draw a better one. The other one was 0.01, so those are 2 boxes up and below. So 1, 2. Two boxes up, 2 boxes below. So this one is wrong. I made 3. And then the last one is also 2 boxes up and 2 boxes below. Now these points are not exactly in the middle of the box, neither are they exactly on the line. So when you use a pencil, you may draw something better. Okay, so those are my error bars. The next thing is I'm going to choose a different color for the line of worst fit. Let me use purple, maybe. So again, you have to look at the points. You have 2 methods that you can start with. You can start by trying to see if you can draw a line from the bottom of the top error bar to the top of the bottom error bar, but putting in mind that the line should cross through all the error bars. If it does, then that line is fine. If it doesn't, then you have to modify the method. So for example, when I try that, if I try the top of the top error bar to the bottom of the bottom error bar, I realize that I may end up leaving out one error bar almost. So let me try to the bottom of the top error bar to the top of the bottom error bar and see what happens. So the bottom of the top error bar to the top of the bottom error bar, it appears as if all error bars are crossed apart from one. So I'm going now to start from the bottom of the top error bar to make this line pass through this point. That will be almost parallel, it will not be good. Let me change the judgment and I say I'm starting from the top of the top error bar, and then the line is going to go through this point here. That is not working. Let me repeat this. The bottom of the top error bar, it passes through this point, it passes here. I think this will be the best. I'm moving from the bottom of the top error, the top of the bottom error bar to the bottom. I'm aiming the bottom of the top error bar, the top of the bottom error bar, and I'm going to aim at the top. So this is not really very good because it has left out this error bar, so I have to change this again. That's the danger of drawing this on a computer. When you try to rub, you may end up rubbing everything. This is really very, very hard. Okay, so I decided to join from the top of the top error bar, and my line goes through. It crosses this point. It crosses this point. It crosses through this error bar. It touches the least point should touch is going to be this one here. What's wrong with this? So the least it should touch is going to be this point here, and then I made sure it touches this point, and then the rule is that it should cross through all the error bars. It should cross through all the error bars. So I try to draw a steeper line, only that because I'm drawing on the computer and my line of best fit is not very accurate, it appears as if they are colliding somewhere, but they are not really supposed to be colliding. I don't think they collide. If you draw a better one, they may meet at some point, but not really colliding. So this is just a rough graph. You can draw a better one. So I will label this to be the line of worst fit, and I will label the blue one to be the line of best fit. Then I have to draw the triangle, so I have to choose 2 points. For example, I'm looking for points where the grid lines perfectly cross at the center. Okay, so I can take these points, for example, this point and this one, and I draw the line of the triangle here. It's not always that you have to draw one triangle, you can draw more than one. Now at the top, I'm just going to use an up estimate that they cross at this point, so that their x and y values are going to be perfectly the same. But when you draw a better line of best fit and with a sharp pencil, they may not cross at that point. So this is just as a guiding tool. So I've chosen a point where the lines are meeting at that point to draw my triangle. So the triangle should be large enough. So that is my triangle for finding the gradient. So from the triangle, I'll read off values. I'll read off the values. Let me write them on paper. So down here, I have this value here, and I have this one for the best fit. So gradient for best fit are the values at this point. For the best fit, we have the x value for best fit is 1.72, and then the x value for the worst fit is 1.73. Then the y value for the best fit is, this is at the center, so it is 1.3. What is that value in the middle? I think it is 1.375. 1.375. So this is best fit, this is worst fit. Then also at the top they have the same x values and y values. So here we have the x value is 2.1, 2.1112, 2.15, 1617, 2.18. So the x value is 2.18 against the y value is this one here, which is 1, 2, 3. So that is 7 times 0.7 times 5 exponent minus 3. Then I add this to 1.8. So this is 1.835. And it is going to be the same for both best and worst fit. Okay, so let me find a gradient very fast. You remember I said your values may be different if you draw a line with a sharp pencil on paper. So let's find a gradient of best fit. And we should find a gradient of the worst fit. And then we find uncertainty. Okay, so gradient of best fit, the y value is 1.835 minus 1.375. 1.835 minus 1.375 divided by the x value is 2.18 against 1.72. 2.18 against 1.72. Then for the worst value, for the worst fit, sorry, there is not enough space here. For the worst fit, the gradient of the worst fit is equal to 1.835 minus, of course, the y value is the same, 1.375 divided by the x value is 2.18 minus the first one for the worst fit is 1.73. Okay, so I expect this to be steeper than the other one, so this second gradient should be bigger. So I'll just check with my calculator. 1.835 minus 1.375 divided by 2.18 minus 1.72. So this is, I'll just write 1.0. Then the second one, 1.835 minus 1.375 divided by 2.18 minus 1.73. So that is 1.02. Okay, then that means the uncertainty. Of course, I did not include the power of 10 when finding the gradient. It is not necessary here. The uncertainty is going to be 1.02 minus 1.00, which is going to be 0.02. So it means the gradient is going to be 1.00 plus or minus 0.02. Okay. Then how many parts are remaining? 3 parts. Okay, determine the y-intercept of the line of best fit. Include the absolute uncertainty. So I'm just going to find C for best fit, C for worst fit, and I subtract the values. So I'll say C for best fit. Of course, here you have to use the equation of a straight line y is equal to mx plus c. So C for best fit is going to be equal to, I'm making C the subject, so I'm taking the y value. Let me just take this point. So it is going to be y, which is 1.375 minus the gradient, which is for best fit towards 1.00 times the x value, which is 1.72. So that is going to give me C for best fit. Then C for the worst fit is going to be the y value is 1.375 minus the gradient, which is 1.02 times the x value, which is 1.7273. Okay, so I'll check my calculator. So 1.375 minus 1.72. So this is negative 0.345. Then the other one is 1.375 minus 1.02 times 1.73. So this is negative 0.38. I want the same decimal places, so it will be negative 0.390. So that means the uncertainty, I'll just subtract. I'll just say 0.390 minus 0.345. I ignore the negative because I know the uncertainty is going to be plus or minus. So I'll check the difference. 0.39 minus 0.345. So that is 0.045. So that is plus or minus 0.045. Okay. Use your answer to A, C Roman 2 and C Roman 3. Determine the value of N and C. So we are going to determine the value of N and C. Include the absolute uncertainties in your values. So of course we noticed that N was equal to the gradient. So it means I will just write N as the gradient. And my gradient was 1.00. They said include the absolute uncertainties in your value. You don't need to be concerned with the units. So I'll say 1.00 plus or minus 0.02. Then the next one is C. From the first equation, we saw that from our equation from the part A, the y-intercept was log 2 over C. They say that the y-intercept was log 2 over C. The y-intercept was equal to log 2 over C, which means that C is equal to C is going to be, okay, 2 over C is equal to 10 power the y-intercept. That is the ant log. Which means if I want to find C, I get the reciprocal. So C is going to be equal to 2 divided by 10 to the power of the y-intercept. So this will be simply equal to 2 divided by 10 to the power of the y-intercept, which is negative 0.345. So I'll say 10 shift 10 power negative 0.345. Then I set 2 divided by the answer. So it is 4.43. So C is going to be 4.43, but we need the uncertainty. So to find the uncertainty, since I have this as C for the best fit, I'll just find C for the worst fit to make life very easy. C for the worst fit is also going to be equal to 2 over 10 to the power of the worst worst intercept, which is negative 0.390, which is, so this is going to be shift negative 0.390, that is the y-intercept for the worst fit, which is that. Then I will say 2 divided by the answer, which is 4.9. So this is 4.909. Is it 4.909 or 4.91? So I want to find the uncertainty. The uncertainty is going to be equal to 4.91 minus 4.43. 4.91 minus 4.43, that is 0.48. So this is 0.48. So the answer here is going to be 4.43 plus or minus 0.48. Now I want you to know that this C here is the one which is given in the question, but this C here was the y-intercept. This was y-intercept. This was y-intercept for best fit, y-intercept for the worst fit. I normally use the letter C for the y-intercept, so you shouldn't be confused by that C. Okay, we don't need to mind about the units. And lastly, the experiment is repeated. Determine the length L of the rod that gives a value of T of 0.1. So remember we saw that, of course, here now the units are going to be very careful. We have to be very careful with the units. So remember T was equal to, I think it was 2L power N divided by C. C has been quoted in milliseconds, so uniformity of the units is going to be very important. So this means it means L is going to be T times C divided by 2 under the nth root. Of course, we know N, and N was the gradient. Then the units of T and C must be matching, of course, for us to be able to substitute them here. And C, remember, C was equal to y-intercept was log of 2 over C. Okay, so I have to make sure that the units of C are matching. On the y-axis, remember when we got the anti-logarithm. Sorry, I think I missed out something here. When I get the y-intercept, the antilog of the y-intercept, because on the y we had t labeled as t, I think 10 to the power of minus 5 seconds. So it means here when I get the antilog of this, I must multiply this by 10 to the power of minus 5. So the answer here becomes times 10 to the power of 5. So this will also be times 10 to the power of minus 5, which becomes times 10 to the power of 5. When I find the antlog, I think it was 10 to the power of, so when I find the antlog of something, if I find the antlog of say 1.75, it will be 10 to the power of 1.75, then I'll multiply this answer by 10 to the power of minus 5 if I find the ant log of 1.75. So I have to add here times 10 to the power of 5. So this will be times 10 to the power of 5 times 10 to the power of 5. So I'll just say here times 10 to the power of 5. Okay, so I'll substitute here. This will be equal to the root. Of course, n is 1. So it is just equivalent to having no root for my values. Your values could be something like 1 point something or 1.02 and so on and so forth. So this is going to be t. So I'll change the units for t to be 0.10 times 10 to the power of minus 3. Then multiply by c, which is 4.43 times 10 to the power of 5. Then I'll divide this by 2. So from my calculator, this is going to be 0.1 exponent minus 3 times 4.43 exponent 5. And then I divide this by 2. Of course, if I remove the root, it is just 1. It is the nth root. The n is 1, so it is equivalent to taking no root. So this is the same as 22.15 centimeters. So I can check the units. I can also check using another method. Let me try to check using another method. So for example, when we introduce log and make L the subject, so log of L is equal to log of T minus log of 2 over C, then divide this by N when I make a log of L the subject. I want you to also remember that 0.10 milliseconds is the same as 10 times 10 to the power of minus 5 in seconds. So this is going to be the same as log of 10. I'm just taking the 10 because the 10 to the power of minus 5 has already been catered for. Then minus log of 2 over c is the y-intercept, so minus the y-intercept, which is negative 3. The y-intercept is negative 0.3, 0.345. Then I will divide this by n, which is automatically 1. Then I will find the ant log. I will find the ant log of this. So this is going to be equal to log 10 plus, okay, let me first find the log 10 plus, because it is minus negative 0.345. Then I will divide this by, of course, 1 because my n was 1.00. It was 1.00. Then I'm going to find the ant log, of course, because to find L, I will get 10 to the power of the answer. So it is going to be 10 so 10 to the power of the answer, which is going to be 22.13 centimeters. So the answer is the same, and you can verify this from the table. So let's check and see if the answer is almost the same. So let's check and see if our value can make any sense. So I'm saying it is 22.15 centimeters, or you could get 22.13 centimeters. So we can check and see if t is 0.1 milliseconds, which is 10 times 10 to the power of minus 5 seconds. Can L be around 22.15? So let's check from the table. When t is 10 times 10 to the power of minus 5, or which is 10 times 10 to the power of minus 5, we got our L as 22.15. I think it makes sense because t, the values when t increases as L increases. So if 10 is less than 24, we expect L to also be less than 54. So I think the answer makes some sense. Remember when you get the ant log, if remember when you get the ant log of the y-intercept, and the y-intercept was times 10 to the power of minus 5, within the log, I had to multiply by negative 10 to the power of minus 5. But here I don't need to multiply by 10 to the power of minus 5 because here I have got a log of 10, the 10 and I've added 0.345. I divided this by 1.00. Then I got the ant log of the answer here, the answer, the resultant of this. I was not getting the ant log of t alone. So that's why I don't need to multiply by 10 to the power of minus 5 here. So the answer is almost the same, 22.15 or 22.13. Yeah, such a question is not really quite easy, but it's just 1 mark after all. Until next time, if any errors, you can write a message or leave a comment. Bye bye.